So this is an Amana or Maytag refrigerator, electronic control, and basically what we did is the same thing we did with that dryer. We had to do strip circuits of components. The first load would be this Jazz board. So where does power come into the Jazz board? Where does power come into this board?
Red?
From H.
Well, red is a color of a wire, so if you were going to explain to me where it comes in, how would you explain it?
Could it be
L1?
J1?
It's J1, because this is J2, so those are the connectors.
J16, J1, pin 6.
J16, so power comes in here and feeds the board J16, right?
Yes.
Okay, so we need two wires to make power to the board, so is this neutral or line one coming into the board?
No.
So it's line one coming into the board. So the board needs a neutral, so where would that be?
Could it be on J1, 1?
And that's correct, that's J11, that's this blue wire coming in right here.
I guess.
So what you were supposed to do is, one, you're going to look at a load, and our load in this case is the control board, even though the control board, is it a load or a control?
Both.
It's both. What did that dryer have that was very similar to this that was both? What part on the dryer is very similar to this?
The
Timer?
The timer.
Yeah.
The timer had a load, which was the motor, and it had all the switches. Well, the board lights up. That's the load part of it, the brain that causes the cycles and the programs. But then there's relays on this board that they are the ones that are the same as the switches on the timer. They turn parts on and off, and they control them. So the control board is called a control, but it is a load too. I mean, if the board don't light up, it's not gonna work, right? So all you had to do then was to create a circuit, and this one was pretty simple. You just L1, and that came in to a board. And we'll just make a box for a board, and then like before, I put J1-6, and this would be L1 coming in, and then coming off the board would be J11, so J11, and we went out. Do I need to write the J1? Do I need to put J11 and J16 here?
Yeah, it's nice.
Well, because you have the J2 here too, so if I don't specify J1, there's two connectors there. And you don't know, if I say, hey, listen, your machine's not working, I need you to check power to the board. Let me know if the board's got power. And I say, yeah, pin 1 and 6. Well, there's two plugs. Which plug do you want me to do? Oh, the red wire. Well, sometimes there may be more than one red. I see a white wire here and a white wire there. There's more than one white wire. And that one of them's neutral, the other one isn't. So you have to know which one it is. So that would be the power coming into the board. And this is where you would put your meter on the board if your board didn't work. So you see, by breaking these circuits down, then we can use them for troubleshooting. Even though they're not drawn in a straight line, if we straighten them out, we make it a little bit easier for us to see. You wouldn't do this in someone's house. All you're trying to do is just to figure out the different circuits, so eventually you'll be seeing them without having to draw them and do everything else. So let's go to the very next load, and the next load would be what?
The
Defrost.
The defrost heater. Okay, so I'm gonna do line 1 coming in, which would go where again?
6.
Go to the same one as before. So this power coming in feeds the board, but it will also feed our components. And then coming off the board with line 1, it would go to what pin?
The 5.
Pin 5 goes through the thermostat up to the heater, and then the neutral of that heater, which I'll do in a different color, comes out the other side. So what is this orange wire here?
There's another one.
That's like a bypass.
Well, what it's doing is it's monitoring how long the defrost thermostat is staying closed during the defrost cycle. Because if it opens up in 5 minutes, we don't need to stay in defrost for the full 22 minutes of the cycle. So the timer knows, or the control board knows, that, hey, the bimetal opened early. We'll still wait a few minutes before we go into cooling, but we don't need to stay in defrost for a full 20-something minutes if the heater shut off in 5. Because what's it doing? It's just sitting there with no heat. And hopefully, if the defrost thermostat is satisfied, then there should be no remaining ice on the tubing, which is what we're trying to get rid of. So when we draw this, you should have had to add that orange wire in. So we're gonna go line 1 into the board, and we're gonna go L1-6 again. But we're gonna have 2 outputs here. We're gonna have one output on 3, so this is gonna be L1-3, and the other one is going to be L1-5. And so I'll do a different color for this orange wire. Haha, use the orange color, huh? So this one's gonna be the orange wire coming off, and I'll finish that circuit in a minute, but this one is gonna go to the defrost thermostat. So we're gonna go like this. And then from there we go to the defrost heater and to neutral. And then this line's gonna come right down like that. So this board is monitoring it, but how could we use these pins? What could they help us do?
Check ohms, is that what you're asking?
Okay, if we're checking ohms, what are we checking when we're checking ohms? Yeah, on those 2 pins.
The defrost heater and the.
Not the heater. We're only checking the defrost thermostat from those 2 pins.
I'm sorry.
But if we go back a step, remember we said this neutral is here?
Yeah.
Which is pin 1, J11. So if J11, I can go J11, I'll just put it right here, put a meter lead there, and here I would measure what? If I go J11 and J13, what am I measuring from those 2 pins? It's not in my drawing. Look at the schematic.
You're measuring the voltage coming out the board.
I'm not measuring voltage coming out the board. I can do an ohms test from this point.
What was the pins?
Huh?
What was the pins?
J11 and
Yeah,
J13. Well, look, watch.
I
I do J13,
The defrost heater?
and I go here, and I go J11. Very good. So I can ohm out the heater from the board too, separate from the bimetal. So these 2 pins, I can ohm out the heater. These 2 pins here, I can ohm out the bimetal. That way I know which part is faulty, so when I come back, I can take care of it. So you guys see those 2 circuits there? All right, let's go to the very next load. What's our next load?
Condition
And the
board.
board, with the overload.
Well, if we're going this way, the overload's not a load, is it? What does an overload do?
It protects the motor.
Okay, but how does it protect the motor? What does it actually do? It protects the motor, but how does it protect the motor? The overload is simple.
Doesn't overpower, was it like that, or overheat? I can't remember.
The overload is similar to what? We got overloads on
Thermostat.
compressors, right? That's what it is. So it's like a thermostat or a bimetal that it opens and stops power. So if the compressor's not running, if we continue to send power to the compressor, it's not running, we could cause the compressor to burn up inside and everything. So the overload's going to shut off like a thermostat, either through heat or through amperage draw, and it's going to protect the motor from any serious damage. Because if the compressor windings burn, the freon insides burn, we can create phosgene gas or we can create acids, which can contaminate our system even more. So let's go ahead and draw our circuit for the compressor. Where am I going to come in on this one?
I mean, it's,
Okay, so again, we're going in through pin 6, and we're going to go out what?
7.
7. Then we're gonna go up to the compressor here. And then if I change colors, I'm gonna go here and here and out. Pretty simple circuit, right? When you guys first looked at it, it was a little crazy, wasn't it? Like, with all these different directions and everything. So your drawing should look like this. L1 to pin 6, and I'm just gonna put 6 there. I'm not gonna draw L1 6, okay? But coming off is 7, so here we're gonna do 7, L1 7, and that's gonna go to the overload. So I'm gonna go, there are overloads like that, but this is really how our overload would look, like a thermostat. It's gonna go to our compressor, run and start. It's gonna go like this. We're gonna have a capacitor here, and we're gonna have a PTC relay. And then this goes out to neutral. Okay, I'm gonna test the new guy. What is PTC? We talked about it yesterday. If he doesn't know, I'm gonna call out one of you guys. I'm not gonna ask.
Oh. Damn. I don't have the P, I think I got temperature.
How does it
control.
work though, if you can know how it works, but not necessarily the
I
name?
get temperature control?
Anybody else have an answer what PTC stands for and what it is? Come on, I talk about this every time we lecture about electronic control machine.
Positive temperature coefficient.
Very good. Positive, PTC
PTC.
is positive
Protection.
temperature, and I'm just gonna put temp, fish.
Yeah, good.
And basically, it's a resistor. It's a resistor that has a resistance value at room temperature. But then as the temperature changes, the resistance will change with the temperature. But we have two different types of temperature coefficients. We have a PTC, but we also have an NTC. NTC are the sensors inside the refrigerator that usually tell the board what the temperature of the refrigerator is. But PTC is used like in ovens and dryers and stuff like that. So NTC is different from this. PTC is temperature and resistance. When the temperature goes up, resistance goes up. Temperature goes down, the resistance goes down. But NTC is when the temperature goes up, the resistance goes down, or when the temperature goes down, the resistance goes up. So these two go together. Positive means that if the temperature goes up, the resistance is going to go higher. This one here is opposite. When temperature goes up, the resistance goes lower. That's why it's negative. It's the opposite. Now, you guys don't need to know every single one of those resistances, but sometimes someone may say, hey, my refrigerator's not getting cold enough. Well, you want to take that thermistor and you want to find out if the thermistor at a specific temperature is a specific resistance. And you'll find that a lot on the schematic chart telling you at what temperature it is what resistance. Okay? I do know, like, there were certain times when GE had very big problems with their sensors failing to operate properly. And they have one part number for every sensor inside the whole entire fridge. Like, you don't have one for the freezer and one for the fridge, and they're all different part numbers. It's one part you keep on your truck and you use it for almost any one. But a lot of guys will tell you sometimes they'll just go to customer's fridge and just change all of them because they didn't want to come back. And they did have a problem where at one time the production of them weren't the best quality, and they had a lot of failures with those sensors. So that is the compressor circuit. Any questions on that one? No?
Does the NTC only goes on ovens and dryers?
No, because the NTC could be used to tell the refrigerator the temperature. How is this monitoring the temperature? Come on, guys, look at the schematic. How is this thing monitoring the temperature?
By the thermistor?
And where are they located, sir?
J2,
J2 what?
J21 and J21 and J22.
Yeah, J2 1 to 3 and J2 2 to 3. So those are your sensors there. I think I still have the tech sheet open. Let me see here. My mouse not working on the touch panel there, but let's see here. Let me zoom out just a little bit here. So this is the full tech sheet. You guys have a copy of it. So we're looking, I don't know if it's on this page or not, what we're looking for is the thermistor chart. And a lot of times the manufacturer will post the sensor's resistance values based on specific temps. So if we look here, let me just, I don't see the thermistors on here. Now look at that. Isn't that crazy? That's the same refrigerator that we're looking at in the other diagram. That's a pictorial of the same refrigerator diagram. Could you imagine trying to read that? So schematic is so much easier. I don't see the resistance values of the thermistors on here. This is a lot older unit, so I don't know. Oh, here it is right here. I found it. Thermistor. Temperature at 77 degrees, it's 10,000 ohms. At 36 degrees, it's 29,000 ohms. At 0 degrees, it's 86. What is that? PTC or NTC?
Say that again.
Say it again?
I'll zoom in on it.
Zoom in.
Right here. Right here. That's our temperatures and our resistance values for our sensors.
Is it MTC?
It's NTC, very good. Why? Because as the temperature is going down,
The resistance going
my
up?
resistance is going up. So that's negative. They're opposite each other. They're not both going down or both going up together. One's going down while the other is going up. And that's to check temperature. And remember, I said in cooling products, you'll see a lot of NTC. Doesn't mean they won't use a PTC. I don't know why they use one over the other. I don't know the actual engineer of how they make a thermistor. But usually you'll find NTC sensors in a refrigerator. Do you need to know, oh, this is an NTC or PTC? No. But you need to know at room temperature, this is the reading you get, you see this 36 degrees. The only time you would have it at 36 degrees is the refrigerator is at its temperature. The closest you could test it was if you take a cup, you pack it with ice, and then fill the remaining space up with water and stir it for a few seconds. That water be as close as you possibly can get to 32 degrees. And you put that thermistor in there, and that way you can measure it, and you're gonna be really, really close to 29,500 ohms, 30,000 ohms. And why do I say 30? Because 32 degrees is a little bit lower, so I'm gonna go a little bit higher in resistance. But this is how you need to know which way is the resistance going, so when you make the test. You don't have to memorize these numbers because most tech data sheets will have this information. Okay? Any questions on that? No? So let's go back to our assignment. So that was the compressor. Let's go, what's the next component?
Condition motor?
The condenser fan motor. So again, we're gonna go right into the same pin 6, right? And we're gonna go back out 7, but this time we're gonna go condenser motor, and then we're gonna change color here. So let me draw this real quick, and then I got a question. L1, go to the board, pin 6, gonna come out pin 7, and we're gonna go to the condenser fan motor and out. I mean, isn't that a simple circuit? You just got the motor and the board. The same thing with the compressor, really the compressor and the board. Defrost heater just got a thermostat in series with it. When you first look at this diagram, you're seeing lines in all different directions. And it's hard to understand what's going on overall in the schematic. So what you guys need to do is, once you identify what part's not physically working in the machine, then you need to be able to just isolate visually that circuit that I'm drawing. You don't need to do this, but this is just a simple straight line saying, that's that circuit. But once you make all these turns, it gets a little confusing because there's so many lines there. And the more you look at it, the easier this is gonna get. So that's why we're just hitting these diagrams and hitting these diagrams so they become simplified. So I'm just gonna do the mullion heater, which is the next one, right? So the mullion heater is basically the same thing as the condenser fan motor, L1 into the board, which is 6. We're gonna go out 7, and then we just got a mullion heater. Oops, I forgot something, right? What did I forget?
The switch.
Ah, the energy saver switch. So that goes like that, and it goes like that. And this is the mullion heater. So instead of drawing it on the next page, I drew it here. Let me ask you a question. Energy saver switch. Is the contact of the energy saver switch closed or open when you select energy saver?
Closes.
Well, I got 2 different people, closed or open. Those of you who think it's open, raise your hand.
What is energized? Is that was the question?
Then you think it's closed,
What
raise
is
your hand.
energized?
Well, come on, it's either one.
What was the answer? What was the question?
It's open or closed when you select energy saver.
It closes.
So wouldn't it be closed?
It open.
It's open.
It's a
Gotta
part of
be
the
open,
energy
but you
saver.
don't
It's
wanna run
open. Look,
current.
if I close it, what happens?
You're gonna
The heater
plug
comes
in
on.
power on the heater.
So I put it on energy saver. If I turn the heater off, you're gonna save energy, right?
Right?
These heaters use very little electricity. They're very low wattage. They're only there to keep the box warm around the door of the refrigerator where it meets the freezer. It's called a mullion strip. And if you lived in Arizona, we could turn the damn thing on. We don't need it. We don't have the humidity level. We live in Florida. We have to have that thing on even when it's our coldest day. We still have a high humidity in Florida. I mean, it's very rare. We're at very low humidity in Florida. So the thing is the government said, hey, we got to make it more energy efficient, so they put a switch on there. But a lot of people would see that energy saver switch, and they say, oh, I'm gonna click energy saver, and then they call you out because the refrigerator's dripping water and the gaskets are getting moldy and everything else. They say, well, man, you got to turn the energy saver off to turn the heater on. It was confusing. So later they changed it from power saver on to reduce exterior moisture, and you put that selection. And then the other side just said off. Because people didn't understand if they pressed power saver on, it was turning the heater off, and that's how you're saving power. But it didn't come out that way. Customers didn't think like that. So I remember many times back in the 90s going out to calls like this, and the customer said, oh, there's water all over the place. I said, ma'am, you need to hit this switch. And when I hit the switch, that'll reduce the moisture. I know it sounds simple, but you know, customers don't know. They don't know. Problem is they got an owner's manual and it tells them all about this, but customers don't read. How many times have you guys bought something and actually took out the owner's manual, read it from cover to cover? We don't. So let's go on to the next component. What is the next circuit?
The fridge, no, the light,
The lights.
The light.
fridge light
So where's power coming in on my light?
J1
from,
for. Yeah,
from
J1 for.
It's not coming in from
direct,
J14.
it's coming direct from the line.
Okay, but lines going where?
For
H,
J1 and 1.
H
H
to,
J1
H to the
Oh, no.
Fruit lights.
The red.
J16.
J1 4.
Okay, stop. Y'all saying J1, and it ain't J1, it ain't J2.
It comes from the.
It isn't
straight line from
J3.
H,
straight
and
line.
This
it
is what's
goes all
happening.
the way to the switch.
Straight line.
But H is going like here
Yeah.
to one of these switches, either one.
Either one.
They're parallel, so it doesn't matter which one I open. And I'm gonna do all 3 of these because all 3 of these are controlled by this. But it turns on both lights and provides a path here. for the water dispenser. But wait a minute, on most refrigerators, the dispenser, if you open up the door, the water dispenser don't work. If you open the door, the ice motor, the auger motor that pushes the ice out, doesn't work. They don't want it to run with the door open because the ice would shoot out all over the floor. So why is it that you have to open the door to make this water valve work? That's a water valve solenoid, by the way,
It's on the inside.
So you can't, got inside the door.
because it's inside the refrigerator. It's not outside in a dispenser. You have to open the door, and on the side of the fridge, it has a paddle inside the fridge. So it requires you to open the door anyways. So let's take a look at this circuit for a second. We're gonna come in here, and we got two red wires coming off of line 1, and we got two door switches. I'll put DS. And they all meet to multiple light bulbs, and I'll just put them here, 1, 2, and then the water valve dispenser solenoid with a dispenser switch. I'll put D switch, not door switch, but dispenser switch, and they all came out. But there is another line going to J1. You guys were right about J1, but power was not being fed from J1. So why do we have a circuit going to J1?
For
For the board.
This circuit here goes to J1.
see.
So we're gonna come off of this power wire here, and we're gonna go into the board J1, 4, J1, 4. Probably don't remember, but I've talked about defrost systems on refrigerators before. Back in the day, you had a mechanical timer, and when it got to the 8 hours of cooling, it went into defrost for 22 minutes. Again, going back to when the manufacturer tried to make the machines more energy efficient, they wanted to defrost less. We didn't want to defrost 3 or 4 times a day. But now we can go up 3 or 4 days before we defrost. So what happens is this wire, this terminal, is a terminal to the board, so the board knows how many times the door's been open and closed and for how long the door itself was open. If it does that, then it knows, hey, you know, this is a big family. There's, you know, like the Brady Bunch. There's people going in and out of this thing all day. We do need to defrost a couple of times a day because the amount of humidity and moisture that's coming in our box. But what if the customer's on vacation? They went to Disney World for the weekend. Well, nobody opens the door. The board sees that. The board says, we don't need to defrost. We can wait a little bit. But that's what this wire is. This is just a feedback wire that every time a door switch is closed, a voltage is applied to the board here. Now, it may go out to neutral as like a completed circuit, but it goes to the board, and every time it sends voltage to the board, it counts how long it's been sending power and everything else. It's like the refrigerators with water filters in them. That every time you put your glass for water, or every time the ice maker calls for water, the board is monitoring how long that water valve is energized, and it converts time into gallons per minute. And it calculates that over a period of time and says, hey, it's time for you to change your water filter. And that's how the refrigerator turns a little light on, says time to change the filter, because it said X number of gallons of water has been passed through this filter since it was installed. So once you change the filter, you put a new one in, most boards don't know a new filter was installed. You have to go back to the display and reset the board and say, hey, a new filter's been in, restart your counter. Otherwise, it's just gonna say change filter all the time. Because it says, well, I know I changed the filter and the light don't go off. It doesn't know the filter's new. There's no electrical plug on there. Now, GE and some of the other manufacturers now put a coated chip in their filters, and the actual filter housing reads, you know, almost like the sun pass you put on your window and you drive under the sun pass, it you know, takes the toll off by a little sticker or a little device. Well, this way GE can say, hey, that's not a manufacturer filter, and it will not let the dispenser work if you don't use the actual manufacturer filter. Now, in a way, that's causing you to buy filters directly from them so they can sell you filters and not allow you to use that. So what you do is you take your first GE filter and you find out where that chip is and you break that filter open and little scotch tape and tape it onto the new filter. I never thought about that till just now. I don't know if it'll work, but it's something I would try. That way you get away with a cheaper filter and it would think the original filter's in there. So that's all three of these components. Now we have a few more components down here. So what's the next component that we're gonna do?
Freezer light.
Well, the light, we already did the lights. We did the
You did
lights
the
and the
freezer-
and the water
freezer
valve.
The freezer light?
Let's go here before we get over there. We still got two more loads over here.
Oh,
We have a damper.
Damper, you got
okay,
it,
two.
So we got a damper, so power comes in here, goes to my damper, and then depending on the damper switch, what is that switch? Is that a switch a customer can open and close the damper by themselves?
The,
So what is that switch doing?
open and close the tap, depending on the temperature.
You're right in a way, but what is the function of the switch?
Is it acting
It's
like
to
a,
let
like
air in
thermostat?
from the freezer into the refrigerator.
That's what the damper does, but what is the damper switch itself doing? How is it working?
Is it working
Yeah,
like a
beginning.
thermostat?
No. It's working by the damper itself. When the damper's open, this would be in one position. I don't know, normally closed or normally open, it doesn't say. But when it's closed, it would be in the other position. That's how the board knows whether the damper's open or closed, depending on the position of the damper. The damper's just like a little door or flap, and when it's open, it hits the switch one way, and when it closes, hits the switch the other way, and that's how the board knows, okay, stop sending power to the damper motor because we're in the position we want it to be. So that's all the function of that switch is. So it's got two outputs, and depending on where the voltage is coming in from that output, this board knows, okay, the damper's open, you can stop sending power to the damper motor. All right, so that is your circuit.
What's the damper again?
The damper goes between the refrigerator and the freezer. And most refrigerators, they only have one actual evaporator. That's where like all the cooling's created. And that's located in your freezer. Now we have dual evaps and everything else, but most refrigerators only have one evaporator, whether it's bottom mount or top mount. And then the air circulates over that, but that's in the freezer, okay? Now, how do we cool the fridge? Well, the damper is just like a little window. Like when it's cold outside, you don't have your AC on, you open a window and you let the cold air in. If it's too cold, what do? You close the window some. If it's not cold enough, you open the window up more. That's what your damper's doing from the freezer to the fridge. If the fridge is not cold enough, the damper opens up and allows more of the freezer air into the fridge. But once it reaches about 36 degrees, it's going to tell the damper to close, because the fan in the freezer may still be running, cooling the freezer, but we don't want to freeze the milk and our fruits and everything inside the fridge, so the damper will close off and stop sending that cold air into the room. Every vent in that shop is controlled by a damper. If you guys go right outside the door into the main shop and look up, you'll see these ducts with a little motorized linkage that's opening and closing a damper. That's controlling the air in here. We have 3 thermostats in the main shop and one in my office. And you're like 3 thermostats in one room. We only have one thermostat in here which controls this one AC. But that one there has different runs that run across the whole room, and there's a damper for each one. So one side of the room may be colder than the other. You may have a bay door open down there, and that one on the other end is not that cold yet. But the damper on this end will say, hey, it's cold over here, close that damper down. So what it does is it restricts the airflow in at that point once we've reached temperature.
So is the 2 thermistors on the board, that's really opening or closing the damper depending on what temperature?
Well, there's
is
a,
in the
there's
refrigerator.
an incomplete circuit here. What, would say that again now?
Something has to open the damper. Tell the damper to open more
Well-
or less.
That's controlled by the motor through this circuit. But the circuit's not complete, is it?
Right, because the motor has to get.
What are we missing?
The neutral?
We're missing the neutral.
Right.
So where am I getting the neutral?
Is it going straight to J1?
J1 what?
J11.
Okay, very good. Say J11. Just be in that mindset. But yes, this is all connected to one board. They're just two separate plugs on the board, but it's getting its neutral through J11 and out. So our diagram would look like this. Line 1 comes in, it goes directly to our damper motor. Our damper motor has a single pole double throw switch, N, O, and C. NO goes to J27. So we got a board here. So this goes to J27 and NC goes to J26. J26. And then it comes over here to J11, J11, and goes to neutral. Notice that power came in on one plug on that board, but it left on a different plug. You've got refrigerator boards that have 5 or 6 different plugs on there. And a lot of people think, oh, this one part, both are running off that same plug, and it's not always the same thing. This part may go to the board on one plug, but needs another plug to complete that circuit through the board. So even though it's all one board, we have 2 different plugs on there. Okay? Any questions on that? That is that circuit. Now we can do the circuit for the fan motor. And we come in here, red, to the fan motor. And then coming off the fan motor, it goes here. So where do we go from there?
To the J1.
J11 again, and out. So our diagram is line 1 into the evap fan. And then from there, we're gonna go to the board, and that's J28, right? J28, and then we come to J11, J11, and then we go to neutral. Now, here's the hard part for people to understand. Like, oh, I can see it go into the board, but how do you know it comes out on J11? How do you know it doesn't come out on another one? Why did we even come up with J11?
Because it's the only one that goes to neutral.
Okay, but yes, it is the only one that goes to neutral, but how do I know that that motor needs that neutral? You understand what I'm saying?
Because it goes in and has come off from somewhere.
Well, because we're inputting line 1 voltage.
That's
Usually, like of these components, line 1 voltage went into the board, and the board send line 1 to those parts. This is opposite. If you grab this fan motor and went to pull a wire off, you're gonna get shocked because one of those wires is power all the time. Same with the damper. It's the neutral side that's open. It doesn't matter which side of the circuit we open, that part won't run. But you can have voltage to the part, but if the circuit's not complete, we have no current flow, it's not going to run. Okay, so this, I know line 1's coming in. If I got line 1 coming in and I only have a 110 volt, 120 volt unit, I know I need the neutral. But these thermistors, we'll get to them in just a minute, okay? We'll finish the circuit for the ice maker and then we'll do that. Any questions on that fan motor? No? All right. It looks a lot easier than it was, right? A lot of you guys didn't do it or didn't complete it because you didn't know how. But when I draw it, it looks simple, right? It's just a simple board in and part. That's it. That's all it is. So we're gonna go and line 1 comes in where?
checking?
Straight from 8, yeah.
From here, we're gonna go right up to this switch, and that switch will either do freezer light or here. So what is that?
That's a what? What is what?
What is that?
That's a
It is
switch,
What
light
switch?
a door switch.
How do you know it's a door switch?
Cause it's a freezer light, so I'm assuming when the door is open on the freezer light turns on.
Yeah, when you open up the door, it completes a circuit to the light. When you close the door, it completes a circuit to the ice maker. So when the door is open, the ice maker won't work. But that's also, you need to know that, because what if I go to the customer's house and they're saying, my ice maker don't work? And so I'm trying to cycle, you know, some of those ice makers have the jumpers on them, and you jump M to N or T to H, and you cycle the ice maker. You could be jumping it, but if you don't hit the door switch with your hand, the ice maker won't run. So we got one power here or here, depending on what. Look, if we got a fuse in series with that, that fuse is bad, the ice maker won't work. The fuse is on the harness on the ice maker. It's clipped right onto the mold of the ice maker. This is an older Crest half moon shape ice maker. And then we go to the ice maker. Ice maker's got neutral and the water valve. So this circuit looks like this. Line 1 comes in. It goes to a single pole double throw switch. NC and O. NC goes to the freezer light and neutral, and then NO goes to a fuse, and from the fuse it goes to the ice maker. The ice maker has a neutral, but the ice maker also has another pin coming off of it going to the water valve. So the ice maker can send power to the water valve so that the water valve would come in. So the water valve is controlled by the ice maker. This is not the same water valve as this one. This is for your water on the door. This is water for the ice maker. Make sense? Any questions? Yes.
Did you check that fuse with ohms or?
Yes, you could.
You could?
Yeah, I'll show you in a minute. I'll look up something and show you what I'm talking about.
Okay.
Let's just finish this last one here. Okay, so all we need is the freezer and fresh food thermistor. So what are we gonna do?
I guess in this case, power would be going in,
J16,
J16 is correct.
and then
And then I'm going to do this circuit for you because you guys would not know this.
Does it loop?
All right, wait, I'm gonna go. So J11 is here. Why am I doing that? Because these are thermistors. How much voltage does a thermistor get?
120?
No. Come on, guys.
Is it 5 DC?
Very good, sir. 5 volts DC. And then there's 12 volts DC. If you went to my Saturday class, we talked about that. 12 volts DC would go to what components inside the refrigerator? Not this one. 12 volts DC are like your evaporator fan motor, your damper motor, your condenser fan motor. Those are usually variable speed fan motors. Where, again, remember, we're trying to save energy, so we drop the voltage to DC volts, and then we can control the speed of the fan motor. So when the refrigerator is really, really warm, we run these fans at high speed, we draw the maximum amount of amperage. But when we get closer to the set temperature, we slow the fans down. Even these inverted compressors, they run at high speed when the refrigerator's hot. But once it gets a temperature, we slow these components down. Like, if you're in a race car and you're coming up to a stop sign at 100 miles an hour, you can't just stop all of a sudden. So you have to start braking and slowing the car down till you get to the stop sign. And that's sort of what's happening with the compressors and the fan motors. They're running 100 miles an hour, but as they get closer to the temperature we want to stop at, they slow these components down for a little while and they use less energy. Some of these newer refrigerators run 80-90% of the time. And you're saying, but how does that save energy if they're running more? Well, they're using less voltage and they're running slower for a longer period of time. And they said some of these refrigerators, instead of cooling the fridge. They're almost like a dehumidifier where they're absorbing the moisture, but they're not making the box that cold when those fans and compressors are running at slower speeds. But what happens is somewhere on the board, we have to have something called a transformer. And the transformer would be like this. We'd have a coil of wire, which would be coming here. We'd have two lines, and then we'd have another coil here, which would be our step-down transformer. So it's gonna take 120 volts and drop it down to 5 volts. But transformers do not make AC DC or DC AC. They only take whatever come in. If it's AC volts coming in, it will lower the AC voltage coming out. So we need diodes and other things built into the circuit board to then convert it from AC to DC voltage. But this transformer here will then come in and feed like this sensor here or here. You don't see this circuit. This circuit's built into the board. So when you got low voltages coming out, if you got this voltage coming in, I gotta have this low voltage here. If I have 120 coming in, but I don't have this low voltage coming here, the problem is the board.
Yeah.
You need to know these voltages. There's only 2 voltages that most refrigerators use. It's like 5 volts on all the sensors, and it's 12 volts on the mechanical components like fan motors and stuff. There may always be something slightly different. That's why you need to go to the diagram and read the diagram. But that's it. This circuit is just like this. You're gonna bring in the voltage to the board, and this is J16, and this is J11, and this is line 1 in neutral. So that is the power on the board, and then there's a transformer here, and it has some diodes in there converting AC to DC, and it has other components on the board. And then coming off the board here, let's just say for the fresh food thermistor, then off of here is going to be J21, and then this is the fresh food thermistor, and then it comes in and it goes J23, and then if we really wanted, J22 is the freezer, so J22 is the freezer here, and it comes to J23. So J23 has got to be what? We're talking about DC, so that's a little hint to what I'm looking for.
The
Maybe
common.
make it this side.
Common, or we got a battery that's DC, right?
Positive, negative.
Positive and negative. So most likely J23 is the negative, and these two are the plus 5s. So if I wanted to check voltage to my sensor here or voltage to my sensor here, I'd put my red meter lead here, my black meter lead there to check DC voltage. Guys, we're going to continue to do more of these diagrams, so I need you all to be doing the assignments I give you. These lectures alone, you all say, yeah, I understand. And then tomorrow you go and you see the same thing. What did he say? If you don't practice them, you're wasting your time here. Okay? You need to do the work. I need you guys to do the practice so that you can get good at these. Any questions? We just did this whole diagram. Now this was easier than the dryer one, wasn't it? A lot easier. But dryers are easier to fix than refrigerators in most cases.
Does it look like
If we
here?
go back to the freezer light switch and the
The
ice maker.
freezer light switch. Was it this one here?
Refrigerator door is closed, which means the switch to the light is open.
Yes.
But then how does the ice maker get power? Because ice maker runs when the door is open.
No,
It's
ice
closed,
maker
right?
runs when the door is closed.
So that switch is normally open on that side.
Okay, normally open and normally closed. Forget about the door itself. If I was to go to the store and say, hey, I need this door switch. It's gonna have 3 pins on it. Common, normally open, normally closed. So if I test these two, it's open. I check these two, it's closed. Now, on a door switch, your door switch looks like this. And it has a little angled piece here that the door hits. Your pins are here, okay? So the door hits it. So right now, just sitting on the table, this piece is out. So these two are open and these two are closed. When I close the door, I push on this, and now I put the pin in this position, so while this door is closed, the ice maker is getting power. When the door is open, the normally closed is closed. So the word normally closed does not mean when the door itself is open or closed. It means if I was to take that switch out of the appliance and nothing was activating the switch, that contact would be the contact that is closed right now. When I close the door, the normally closed position would now be open, and the normally open position would be closed. It takes a while to understand that normally open and normally closed thing, but you'll get it over a period of time, because like a dryer door switch, is it normally open or normally closed?
Normally closed.
It's normally open. Because once I close the door of the dryer,
Or it should be
the
closed.
dryer can run. So I'm closing the door switch so that it completes the circuit so the dryer will run. When I open the door switch opens. When the door is open, that is the normal position of the switch. There's nothing pressing on it.
But when you close the door, it closes the switch, it closes the circuit.
So the switch was normally open. When you close the door, now the door closes the switch.
So it's what it does at rest without any external.
Yeah, without anything pressing on it, that's what normally closed means. Its contact is closed outside of the machine, okay? What about the door switch on an oven? Is it normally open or normally closed?
Would it just be normally open? Wouldn't door switches just be normally open in general?
Well, what happens when you open the oven door?
They don't stop.
It releases?
It's open.
The light comes on in the oven.
Yeah, but the heater's still going.
Well, the heater has nothing to do with the door being open. When you broil, you crack the door open anyways, right? So the door switch has nothing to do with the elements. Now, if you have a convection fan, when you open the door, the fan stops. But most door switches in an oven are normally closed switches. So when I open the door, the switch closes, so the light comes on inside. Now, there are some switches that have more than one pin. Some of them have a normally open position, so when I close the door, it closes. I gave you one example, would be the convection fan motor. If you're convection cooking with the fan on, they don't want it to open and have that fan blowing 500-degree air onto the customer. So they open the door so the fan stops for safety, okay? So there is a normally open position that closes when I close the door too. Give me another example of where we would use that same contact. What else would we use that contact for in an oven door?
Right off the top of my foot.
Like another appliance?
In an oven door. The same thing we're talking about. One is for the light, one is for the fan motor. So when I open the door, the light comes on, but the fan stops. I close the door, light goes off, fan starts running. What other component is dependent on that switch?
The heater.
The door lock mechanism for self-clean. If you don't close the door and activate the switch, the board will not lock the oven to clean. So there's a contact that's normally open, not for the light. There's a contact normally open that's for the convection fan motor, but it also, when it closes, the board sees that. A lot of times that switch isn't directly in series with the light or directly in series with the lock. Like this, well, this switch is in series with this, or this switch is in series with that. We may have a board and it has a switch here that the board sees if the switch is open or closed, and if it's open, the light comes on. If it's closed, the board will have the lock motor over here and tell the door to lock. But it does not want the lock motor to lock with the door open, because what'll happen is that lock comes over with the door open, and you close the door and you're gonna hit it with the door and you're gonna chip the porcelain on the door and everything. So they don't want that lock to lock. Plus, you don't want the lock to lock with the door open, because then it'll allow the oven to self-clean. And that gets up to about 850, 900 degrees. We don't want that to happen with the door open. So that switch has multiple functions. It may be one contact, open or closed. But it does many different things. So when you guys are working on machines, one of the things I say is, don't just take it apart and put it back together. You have to know the function of every part. The more you understand the function of every part and where it is and what it does, the easier it is to troubleshoot. If you don't know those parts and what they do, then how do you know if it's good or bad? Or how do you know to test this switch, even though this motor don't work, it may be because this switch, which is another part of the circuit. Any questions? Any more questions?
So you see how you said the refrigerator door switch is open, and then when you open the door, it closes to turn on the light?
That's correct.
So that switch, technically, if the refrigerator door is always closed, that switch is always open. The other switch
Yes.
is like the freezer light switch and the damper switch. Is it safe to say that those switches technically are always closed? They're just in
Well, no,
one
you have
position
a
or
normally
another?
closed and a normally open position, but when the door's closed, the normally open is closed and this one's
That's what I'm
open.
saying, like, but at the end of the day, like, one of those switches is always.
One
like,
switch is
closed.
always gonna be open on a single pole, double throw. Single pole, double throw. Throws are, what direction is it gonna send power? The pole is what that switch is swinging on. So power's usually coming in on the pole and going out to one of these. In a single pole, double throw switch, one of them is always gonna be open. If the door's closed, the normally closed is open. If the door's open, the normally closed is closed and the normally open is.
Well, could you say the same
Whatever.
thing, that one of the switches is normally closed too?
Which switch?
So for example, like the freezer light switch, for example, when you open the freezer,
This switch.
yeah, when you open the freezer, it closes, turning on the freezer light, right?
That's
But
correct.
when you close the door, the switch moves and it closes to turn on the ice maker. So
That's
technically,
correct.
that switch at one point is either always open or always closed. It's vice versa.
Yes, there's always one contact that's open, always one contact that's
On
closed.
on that type of.
Yes,
Cool.
that's what a single pole double throw switch is. It sends power to one or the other depending on what mechanism is activating it.
And the other type of switch is,
Normally open or normally closed, because it only has two terminals. So it's either open all the time until something hits and closes it, or it's closed all the time until something hits and opens it. Okay? Any other questions on any of these other ones?
why does a freezer thermometer and a fresh food thermistor and the freezer thermistor look like a heater?
Because they are resistors, and a heater is technically a resistor. When you push current through a resistor on a board, the resistor gets warm. A heater is really a resistor. It's just higher voltages and amperages, which gets more heat. So the symbol for a heater and a resistor, it was in that basic electricity book you did with all the symbols.
Yeah, they look different. Like a thermistor is the same heater, but it has like a circle around it and a T.
Well, because it's a variable resistor. In other words, the temperature, it changes resistance. It's not a constant resistor. Like a bake element is always 30 ohms. But a thermistor, we go back to this chart we were looking at, and at 77 degrees it was 10,000 ohms, but at 36 degrees it was 29,000 ohms. So its resistance varies. So by showing you a resistor but putting a T on it, it just lets you know. In this case, they didn't even go that far. They just drew resistors. You're supposed to know what a thermistor does. You're a technician. You know, remember, when manufacturers draw these diagrams, they're not looking for the rookie that just started working on this. They're assuming you're a technician that knows how to read these diagrams, and you see that you know what it's about. I told you before, I look at these diagrams and I can tell you actual function of the machine and what everything's doing. Yes, I've been doing it for a long time, but it's the same thing. You know, I speak a little bit of Spanish, but I don't speak that good of Spanish. So I need to keep practicing it till I get better. You guys need to speak wiring diagram language. So you come here every day and you're gonna do something with the diagram. Even if you're just working on a machine and you're looking at the diagram and working on the machine, that's what's gonna make it easier for you guys. There's no quick answer that says, okay, I'm gonna give you this one assignment and you're gonna understand diagrams forever. You know, some of these videos that I post online, watch them 2 or 3 times. Not like today watch it and then tomorrow watch it next day. Watch it and go back a week later and don't watch it 100%. I know Josh can't do that. Josh, his attention span is only so much. But the thing is, he'll fast forward to one part and stop and watch that one part. And then sometimes when you watch it a second time, things come to you, say, oh, you know, I didn't realize that the first time I saw that. And it makes more sense. So these diagrams are how you're going to learn it, is we're just going to keep doing these things. And again, I keep doing them differently, like draw these circuits and do this and do that, so you can see what we're really looking at. Any more questions, guys?
When you check the thermostat, when you check it from.
The thermostat? What thermostat?
Thermistor.
Oh, thermistor, okay.
Sorry.
Which one specifically? We have 2,
The
freezer and fresh
freezer.
food? So we're checking the freezer thermistor, this one right here?
Yes.
Okay, so
when
what's
you-
your question?
So when you check it from J2 pin 2 and J2 pin 3?
That is 100% correct.
Okay, cool.
What if I'm checking the fresh food thermistor?
It'll be J2 pin 1 and J2 pin 3.
Perfect.
Okay.
You're getting it. You're getting it, come on. You've got a few good answers. All right, guys, shop work.
Can you show me